块，懂吼？来，再一个，你知道我在讲什么的？我觉得这样比较有数学的感觉哦。黑色3块，啊，中间那点点点。另外一个极端的情况就是每一块都涂成什么色？黑色，所以这个时候叫黑色几块 ？n 块。那我们现在来看一下哦，当我进行分类之后，我现在就把它切割嘛，反正2的 n 次方很多嘛，对不对 ？n 是某个正整数嘛，我这里有 n 个方块，对不对？来，请问你黑色0块代表说全部都涂成白色，情况有几种？一种，这个叫 Cn 取什么 ？Cn 取0啊，0个方块涂成黑色嘛，就是每一个都白色啊，情况就一种啊。那请问你黑色有一块，这个叫什么？这叫 Cn 取1啊 ，n 个相异的方块选一块出来涂成黑色嘛，啊其他都白色嘛，这种情况几种？有 n 种嘛，对不对？那黑色有2块的情况叫做 Cn 取多少？2啊，那黑色有3块呢 ？Cn 取3啊，那最后点点点 ，Cn 取 n， 从这个地方你很容易去理解。来，请问你，根据加法原理，这些都互斥哦，互斥哦，对吧？它们不可能同时发生，所以你把它加起来 ，Cn 取0加 Cn 取1加 Cn 取2，一直加到 Cn 取 n， 会等于多少？2的 n 次方。这东西要理解的，好不好？可以吗？那不管你是用这种什么带 k 带1去理解，还是用这个例子去理解，随便你。但是这个等式很重要，好，这个等式很重要，这样可以吼？行不行啊？你们这个不行啊？这样就差不多了。
难道你赶科吗？
好，我给你们看一个影片，这个影片看完我们就休息了，好不好？来，那个苏轩帮我拍一下电脑。
不觉得好吃。然后你拍了，人家不能上传。真不好吃。
你是数学形状。
有那么那个吗？看一下那个。
今天午餐吃什么吗？
今天午餐吃好料的。肉羹应该是吧？
肉羹。
好料的切。
肉羹
三色豆。
三色豆。青椒的切的。
这个不错啊，给你们看，看一下。你现在值得一看啊。
看影片都觉得累。
Arranged stack but it's actually a mathematical treasure trove. Indian mathematicians call it the staircase of Mount Meru. In Iran, it's the Khayyam Triangle, and in China, it's Yang Wei's Triangle. To much of the Western world, it's known as Pascal's Triangle, after French mathematician Blaise Pascal, which seems a bit unfair since he was clearly late to the party, but he still had a lot to contribute. So what is it about this that has so intrigued mathematicians the world over? In short, it's full of patterns and secrets. First and foremost, there's the pattern that generates it. Start with 1 and imagine invisible zeros on either side of it. Add them together in pairs, and you'll generate the next row. Now do that again, and again. Keep going, and you'll wind up with something like this. Though really Pascal's triangle goes on infinitely. Now, each row corresponds to what's called the coefficients of a binomial expansion of the form x plus y raised to the n, where n is the number of the row, and we start counting from 0. So if you make n equal 2 and expand it, you get x squared plus 2xy plus y squared. The coefficients, or numbers in front of the variables, are the same as the numbers in that row of Pascal's triangle. You'll see the same thing with n equals 3, which expands to this. So the triangle is a quick and easy way to look up all of these coefficients. But there's much more. For example, add up the numbers in each row, and you'll get successive powers of 2. Or, in a given row, treat each number as part of a decimal expansion. In other words, row 2 is 1 times 1 plus 2 times 10 plus 1 times 100. You get 121, which is 11 squared. And take a look at what happens when you do the same thing to row 6. It adds up to 1,771,561, which is 11 to the 6th, and so on. There are also geometric applications. Look at the diagonals. The first two aren't very interesting. All 1s, and then the positive integers, also known as natural numbers. But the numbers in the next diagonal are called the triangular numbers, because if you take that many dots, you can stack them into equilateral triangles. The next diagonal has the tetrahedral numbers, because similarly, you can stack that many spheres into tetrahedra. Or how about this? Shade in all of the odd numbers. It doesn't look like much when the triangle's small, but if you add thousands of rows, you get a fractal known as Sierpinski's triangle. This triangle isn't just a mathematical work of art, it's also quite useful, especially when it comes to probability and calculations in the domain of combinatorics. Say you want to have 5 children, and would like to know the probability of having your dream family of 3 girls and 2 boys. In the binomial expansion, that corresponds to girl plus boy to the 5th power. So we look at the row 5, where the first number corresponds to 5 girls, and the last corresponds to 5 boys. The third number is what we're looking for. 10 out of the sum of all the possibilities in the row. So 10 over 32, or 31.25%. Or if you're randomly picking a 5-player basketball team out of a group of 12 friends, how many possible groups of 5 are there? In combinatoric terms, this problem would be phrased as 12 choose 5, and could be calculated with this formula. Or you could just look at the 6th element of row 12 on the triangle and get your answer. The patterns in Pascal's triangle are a testament to the elegantly interwoven fabric of mathematics, and it's still revealing fresh secrets to this day. For example, mathematicians recently discovered a way to expand it to these kinds of polynomials. What might we find next? Well, that's up to you.
不错不错。好，谢谢各位同学啊，这个影片不错，影片不错。好，大家休息一下，谢谢谢谢。巴斯卡三角形很有趣啊，哈，这个
聪明对，我们应该证明他在讲聪明，他就把它说错了。